You might say that weather is what flying is all about. It sure has a big effect on every trip we make. Jeff is going to use some nifty animation to teach you about the theory of weather. Then he'll go over all the different reports and forecasts you'll encounter when making your own weather decisions.
What causes weather? The answer is solar energy. The sun's rays strike the earth and warm the surface, either the ground or the water. An area of the earth's surface affected by the sun can be called a source region. That source region affects the air above it. That body of air above the source region is called an air mass. Air masses take on the characteristics of the source regions below it. A polar maritime air mass, for example, takes on its characteristics over a large, cold area of water. A tropical air mass starts over our hot region of the Earth. As these air masses move, they're slowly changed by the Earth's surface over which they move. This change is called modification. Air mass modification results in the weather that we see and that we fight with during instrument flight. For example, if a warm air mass from a tropical region moves over a cooler land mass, the warm air will cool and its moisture will condense into clouds or precipitation. Air is made up of molecules and therefore has weight. Air also exerts pressure, as you know from blowing up a balloon. Depending on temperature and how many molecules are present in a given space, its pressure will vary. Consequently, air pressure varies around the Earth. This difference in pressure is called pressure gradient. The pressure gradient is what causes the air masses to move away from their source regions. The higher pressure tries to move into the low pressure. These movements of air, resulting from the pressure gradient, are what cause wind. The stronger the pressure gradient, the stronger the wind. We see here a representation of air pressure differences on the Earth's surface. These lines are called isobars. Iso means equal, so isobars connect points of equal barometric pressure in a similar way that contour lines on a topographical map connect points of equal elevation. The tendency is for the air to move directly from a high pressure area to a low. The wind is not straight, however, because it's modified by two things, Coriolis and friction. Coriolis is a force caused by the Earth's rotation that deflects a body in motion, or in this case, wind, to its right in the northern hemisphere or to its left in the southern hemisphere. When air moves from a high to a low pressure area, it's deflected to the right until it runs parallel to the isobars. Besides Coriolis, friction is another force affecting wind. Air molecules are in friction with the Earth's surface. This friction causes the movement of the air to be deflected from parallel to the isobars to crossing the isobars at a 30-degree angle. The friction layer is usually 2,000 feet thick from the ground level, and above that, the air movement is not affected. Winds above this friction layer are called winds aloft. They would be parallel to the isobars. Let's put this in perspective for the pilot. Some charts will describe air movement at a certain altitude. You need to know that the direction and speed of the wind will change from winds aloft to on the ground. As a rule of thumb, when going from winds aloft to surface wind, the direction will change 30 degrees counterclockwise and the speed will decrease to 40%. So if the winds aloft were 100 knots, the surface wind would be 40 knots. Weather people, and therefore pilots, frequently use the term standard conditions. A standard condition is just an arbitrary point of reference used to describe temperature and pressure. There are standard conditions at any altitude, but they're usually stated at sea level. They then can be adjusted to any other altitude. The standard temperature at sea level is set at 15 degrees Celsius or 59 degrees Fahrenheit. Normally, the temperature cools by 2 degrees Celsius per 1,000 feet of rise. This rate of change in the temperature is called the lapse rate. But the lapse rate isn't always the same. Sometimes, instead of cooling by 2 degrees per 1,000 feet, it actually warms as you climb. That's what an inversion is, warmer air over cooler air. Now, using what we know so far, it's an easy process to determine the standard temperature at any altitude. The formula is double the altitude, subtract 15, and change the sign. Or in other words, if it's a minus, change it to a plus, or if it's a plus, change it to a minus. Let's look at an example. At 10,000 feet, we would double the 10, giving us 20, subtract 15, giving us 5, change it to minus 5, so the standard temperature at 10,000 feet is minus 5 degrees Celsius. Or another example, 22,000 feet. Double 22 is 44. Subtract 15 from 44 is 29. Change the sign to minus 29. The standard temperature at 22,000 feet is minus 29 degrees Celsius. And this can be used for any altitude. So much for standard temperature. Now let's look at standard pressure. The standard pressure at sea level is defined as 29.92 inches of mercury, or that means that the weight of a column of air on a standard day equals the weight of 29.92 inches of mercury. The pressure decreases by 1 inch of mercury per 1,000 feet of rise. Therefore, the standard pressure at 1,000 feet above sea level would be 28.92, and so on. So 1 inch equals 1,000 feet, 1/10 of an inch equals 100 feet, and 1/100th of an inch equals 10 feet. You'll sometimes see the term pressure altitude. This is just the altitude based upon that standard plane of 29.92. Now, the 29.92 inches of mercury datum plane can either be above actual sea level or below actual sea level, depending upon the day. Anytime you have 29.92 dialed into your altimeter, you're reading pressure altitude directly from the gauge, because you're basing it on this arbitrary plane rather than some actual conditions. Now, if you ever go outside of the U.S., you may see the pressure listed in millibars rather than inches of mercury. Millibars are just another way of describing air pressure. Standard conditions at sea level, remember, is 29.92 inches of mercury. Well, standard conditions in millibars is 1013.2. There are charts that will convert millibars to inches of mercury and back again. There are also some altimeters that have both millibars and inches of mercury on their faces. Now let's take a look at what non-standard temperature and pressure will do to altitude. On a standard day, you're flying at an indicated altitude of 10,000 feet. Your true or actual altitude would therefore be 10,000 feet. Now, if you were to change the temperature of the air you're flying in to something colder than standard, your instrument would still be indicating 10,000 feet, but you would actually be lower than that because the air density has changed. The weight stays the same, but the column height has diminished. Or if you were to change the temperature to something higher than standard, you would actually be higher than indicated. Remember, all three aircraft in this example are indicating the same 10,000 feet. The dangerous situation is when you're actually lower than indicated, since you're closer to the ground or some obstacle. That's why we use the saying, from high to low, look out below. This holds true for going from high to low temperature and high to low pressure. Relative humidity is a term that we're probably all familiar with. This is simply a comparison of the amount of water vapor actually in the air with the amount of water vapor that the air could hold at that temperature. It's expressed in a percent form. For example, 100% relative humidity, also called saturated air, means that the air at that temperature is holding as much as it can. The amount of water vapor air can hold depends solely on its temperature. If you increase the temperature, you increase the amount of water vapor it can hold. If water vapor is added to saturated air, or the air temperature is cooled, some has to precipitate out in the form of dew, rain, or clouds. The dew point is a temperature to which you must cool air so that it will reach 100% relative humidity or saturation. If the temperature is above the dew point, the air can take on more moisture. If the temperature is at the dew point, the air is fully saturated. If the temperature drops further, or if more moisture is added to the air, something has to give in the form of either clouds, condensation, or rain. The temperature dew point spread is the difference between the actual temperature and the reported dew point. It's another way of expressing relative humidity. If you see a spread of 50-48 on a weather observation, you know the air is humid. If you see 50-30, you know it's dry. With a 2-degree spread and light wind, fog is often possible. A 20-degree spread means that there'll probably be no problem with fog. There are 2 ways that water vapor can be added to the air: evaporation and sublimation. Evaporation is when water goes from the liquid state into the gaseous or vapor state. Sublimation skips that liquid state altogether. In other words, it goes from the solid state directly to the vapor state. In other words, you have ice that just shrinks because it's so dry it goes right into water vapor without getting into slush or the liquid state at all. Air masses will either have this tendency to be stable or unstable. If you were to move air upwards, such as up a mountainside, and it stayed where you moved it, it would be considered to be stable. If instead the air was unstable, it would keep on moving upwards after you gave it its upward nudge. Some general properties exist depending upon the air mass's stability. Unstable air tends to have cumuliform clouds, which are puffy cotton ball types of clouds, and thunderstorms. Any precipitation will be in the form of showers. There will usually be rough air, and visibility will be good, except in blowing obstructions. Stable air, on the other hand, is characterized by stratiform or layered clouds. Precipitation will be continuous, the air will be smooth, and visibility will be fair to poor because of haze or smoke. We'll see later how the instability of an air mass enters into the formation of thunderstorms. We've just spoken about types of clouds, so let's look at how weather people classify clouds. Clouds are broken down into 4 families which are determined by their height. Low clouds occur from the Earth's surface to 6,500 feet. Middle clouds occur from 6,500 to 23,000 feet. High clouds occur above 23,000 feet and are made up of ice crystals. The 4th family are clouds that occur within 2 or more of the above classifications. These are said to be clouds with extensive vertical development. The word nimbo or nimbus attached to any cloud name, such as cumulonimbus, just means that it's a rain cloud. Curved lens-shaped clouds are called lenticular clouds. They're associated with a wind over a land obstruction, such as a mountain range. They look stationary, but are continually forming at the leading edge and dissipating at the trailing edge. If you see lenticulars, it's a sure sign of turbulence. Any turbulence will usually be below them in the roll clouds. Pilots often talk about the base of the clouds and hundreds of feet above the ground, and that's where you'll hear the term ceiling. A cloud ceiling is the base of the lowest layer of broken or overcast clouds that are not classified as thin or partial. Various ways are used to measure the height of a ceiling. They may be reported by aircraft, estimated by a weather observer, or actually measured by bouncing a light beam off the base of the clouds, as long as the clouds aren't too high. Now there's a method that we can use to estimate the base of cumulus-type clouds as long as we know the temperature and dew point. You simply take the temperature dew point spread and divide it by 4.4, giving us the base of cumulus-type clouds in thousands of feet above the ground. For an example, let's say the temperature was reported at 90 degrees, and the dew point was reported at 46 degrees. Simply subtract 46 from 90, giving us 44. We take the spread and divide it by 4.4, giving us 10. So the base in this example would be 10,000 feet above the ground. Next we'll move on to fog. Fog is merely a cloud within 50 feet of the ground. The types of fog depend upon their method of formation. Radiation fog forms over flat land on clear, calm nights. The heat of the day radiates from the earth, cooling the earth and the air above it. Advection fog, also called coastal fog, is formed when a wind blows moist, warm air over a colder surface. Upslope fog forms when a wind blows moist air up a slope. This movement up a slope is called orographic lifting. Two other types of lifting action are thermal, such as over a parking lot or a dark plowed area, and frontal, when air is pushed up the slope of a front. Notice that both coastal fog and upslope fog require a wind. And finally, industrial fog, or also called smog, is formed when condensation nuclei are present, such as smoke or soot particles, enabling moisture to form on the particle. Thunderstorms are the last cloud type that we'll discuss. This is a symbol found on weather maps for thunderstorms. Now, the FAA likes to ask what is always present during a thunderstorm. Well, the question is, what causes thunder? Lightning causes thunder. So lightning is always present in a thunderstorm. There are three things that are required for the formation of a thunderstorm: unstable air, high relative humidity at all flight levels, and some form of lifting action. Remember, the three types of lifting action are orographic, frontal, and thermal. The cumulus stage is the first step of a developing thunderstorm. The instability of the air has formed a column of updrafts, and the water vapor in the air is condensing to form droplets. As the droplets are kept aloft by the air currents, they become larger until they're too large to be kept aloft. They start to fall within the cloud and start the formation of downward air currents as they drop toward the ground. The mature stage starts when this rainfall first reaches the surface. The shafts of upward and downward moving air currents create severe turbulence. Some water droplets are kept in the air for such a long time that they freeze into hailstones. Depending on the strength of the updrafts, these hailstones can become quite large. The updrafts use up the available heat energy in the area and are replaced almost entirely by downdrafts. The third stage, dissipating, is composed entirely of downdrafts. The characteristic anvil top forms from the action of the upper level winds on the cloud. This anvil points in the direction of the movement of the thunderstorm, not from where it came. Hail is often found in the anvil, and it can fall in the clear area below. A group of thunderstorms that form in a line are called squall line thunderstorms. They usually form in front of fast-moving cold fronts, but can actually form anywhere that there's unstable air. These are extremely dangerous and should be avoided at all costs. Another type of thunderstorm you might hear are called embedded thunderstorms. These are just normal thunderstorms, but they form in a general cloud area so that they're embedded in other clouds. Because they're hidden by the poor visibility in the area, they're sometimes difficult to discover and avoid. As I mentioned before, the turbulence associated with a thunderstorm can be quite intense. Rough air can be found in all areas of the storm, but the roll cloud on the lower leading edge has some of the worst. The best plan of action for a pilot is to go completely around the storm. In fact, the FAA says that you should avoid thunderstorms by 20 nautical miles. You don't want to try to go underneath a thunderstorm because the downdrafts could force you into the ground. Have you ever heard the term microburst? This is a term describing intense downward moving shafts of air below a thunderstorm. They've only been recently understood, but in fact they've been around since the time of Noah. These microbursts can become so strong that they can force large aircraft, even airliners, into the ground. Now, virga is another term you might hear. And these are rain shafts that leave the cloud but evaporate before reaching the ground. There are a few steps you should follow if you're ever caught inadvertently in a thunderstorm. First of all, don't turn around. Go straight ahead. You should set your power for recommended turbulence penetration speed and maintain a level attitude. Don't fight for altitude, attitude. This chart shows the FAA's description of turbulence intensities. Light turbulence causes slight changes in altitude or attitude. Moderate turbulence is greater than light, but the aircraft remains in positive control at all times. If you hear light or moderate chop, this is just rhythmic bumpiness rather than the roller coaster ride of turbulence. Severe turbulence causes large variations in airspeed, and the aircraft may momentarily be out of control. In extreme turbulence, you're violently tossed about, and the aircraft is impossible to control. There also may be possible structural damage. I've mentioned fronts before. Let's look at them in more detail now. Fronts, or frontal zones, are defined as a line of discontinuity between two dissimilar air masses. Now, what this means to a pilot is that there's warmer air on one side and colder air on the other side of a front. The name of the front comes from which side is winning the battle or gaining ground. Some general characteristics of all fronts are: one, as you cross a front, there is always a wind shift to your right. And two, if you are watching a barometer, frontal passage is when the barometer reaches its lowest value. A cold front is formed when a colder air mass moves underneath a warmer mass. The slope of the front looking from the side is relatively steep, making the warm air cool quicker as it rises and creating a relatively quick, intense frontal zone. The average cold front moves quicker than a warm front, and the weather clears up quicker after frontal passage. Cold fronts are shown on weather maps as a line with sharp teeth pointing in the direction the front is moving. During warm fronts, the warmer air rides up over the colder air and pushes the colder air backwards. Surface friction tends to slow down the cold air's retreat, creating a relatively shallow slope when viewed from the side. The weather patterns created by a warm front are not as severe as by a cold front, but any given spot on the ground is affected for a longer period of time. A warm front is shown on maps as a line with rounded bumps pointing in the direction the front is moving. A stationary front is just that, stationary. Neither side is gaining. These come about when a warm front or cold front slows down and stops. For example, a cold front might have stopped, turned into a stationary front, and then turned into a warm front. The slope of the front varies with wind distribution and air density. They're shown on maps as a line with the bumps and teeth on different sides. An occlusion or occluded front is simply the collision area between two different fronts. When a cold front overtakes a warm front, the warm air in the middle is forced up away from the surface. The weather around an occlusion is usually a combination of weather from the warm front and the cold front. The slopes vary depending on the relative strength of the air masses. They're shown on maps with the bumps and teeth on the same side of the line. The next thing I'd like to talk about is something that's really dangerous to light aircraft, and that's icing. The danger comes from three areas. It changes the shape of the airfoil, wing, and tail, allowing less lift to be produced and producing more drag. It adds weight to the aircraft surface, and as ice comes off the aircraft or is thrown off by the prop, it can damage other engines or the plane itself. If you were caught in icing conditions, you would probably first notice ice forming on some protruding object, such as an unheated pitot probe. Now, if you ever do get caught in unforecast icing conditions, you need to report that to air traffic control so they can warn others. Aircraft icing, like most everything else, comes in several different forms. Rime ice forms from small water droplets that freeze upon impact and builds out into the wind stream. This causes it to change the wing shape more than other types and decrease the lift produced by the wing more. It traps air as it freezes, giving the ice a milky appearance. Rime ice is relatively brittle, making it easy to remove with de-icing boots. Clear ice, on the other hand, forms from large water droplets. The water hits the surface, starts moving back over the wing, and freezes as it moves. Clear ice is transparent and relatively hard and adds more weight than rime ice. Since it doesn't form mainly over the leading edge, it's difficult to remove. Mixed ice is a combination of rime and clear ice, and it's probably the type of icing that you'll most likely run across. Now, frost occurs when water vapor goes directly from the vapor state to the solid state. The dew point needs to be below freezing, and the surface of the wing needs to be below freezing for frost to form on a wing. It doesn't look that dangerous, but it really is, because it roughens the wing's surface, so the wing produces less lift. Now let's talk about freezing rain, an extremely dangerous form of ice because of the heavy ice buildup. It occurs when you have warmer air above freezing air. Water forms in the warm air, falls and reaches the cooler air where the airplane is, freezing upon impact. Freezing rain has the potential of forming the greatest accumulation of structural ice. If you get caught in it, climb into the warmer air if possible. This will put you in the area where it's merely raining. If you don't have the power to climb out of it, then land or turn around. Ice pellets form with freezing rain, but at an altitude farther into the freezing layer. The rain has had more time to freeze since you're lower in the cold layer. It poses no danger as long as it remains pellets. It's an indication that there's freezing rain above you and warm air above that. The FAA has standard terminology in describing icing intensities, just like it does in describing levels of turbulence. All the different intensities have to do with the rate of accumulation of the ice. The intensities are trace, light, moderate, and severe. A trace is when icing becomes first noticeable. It's not hazardous, even to aircraft without icing equipment, unless it's encountered for long periods of time. Light icing may create a problem to light aircraft. It poses no problem to aircraft with icing equipment. Moderate ice accumulates quickly and requires the use of icing equipment. Severe icing is hazardous to all aircraft. The last item that I'll cover here is the difference between de-icing equipment and anti-icing equipment. De-icing equipment is designed to be turned on after the ice forms and break it off. An example would be de-icing boots on the leading edge of wings. Pressurized air is used to fill the rubber chamber, expanding the boot, breaking off the ice after it forms. Anti-ice equipment is designed to be turned on before the ice forms. An example would be hot air from an engine or electricity heating up the surface, not allowing ice to form in the first place. Now let's move on to another section that is dangerous to all aircraft, and that's wind shear. It's defined as a sudden change in wind speed or direction, and it can occur horizontally or vertically. It can be associated with low-level temperature inversions, jet streams, frontal zones, or near thunderstorms. Remember we talked about the fact that the wind always shifts when you cross a front? Well, that property often causes wind shear along the frontal zone. When a warm front passes, the wind shear occurs before the front passes a point on the ground because the frontal zone is leading the spot where the front touches the ground. With a cold front, it occurs after the front passes a point on the ground. Wind shear only becomes dangerous when you're close to the ground. This is because of the slower air speeds and you have less altitude to get out of the shear. Usually, higher up is no problem. Now let's look at two different types of wind shear that you might find while on final. The first one is called a performance decreasing shear, which is a horizontal shear and will occur if the headwind decreases while you descend to the runway. As you pass the shear zone, the relative wind decreases, causing the airspeed to decrease and the aircraft to descend below the desired flight path. You will add power and bring the nose up to regain your flight path, and this sometimes causes a hot or high final approach. The second type of shear you might encounter is the performance increasing shear. You start out in a tailwind and end up in a headwind as you touch down. As you pass the shear zone and the relative wind increases, your airspeed will increase and you'll climb above the desired path. You'll correct back by decreasing power and lowering the nose. Be careful not to decrease the power too much though, or you'll go through the path and land short. The best way to recognize a shear on final is to monitor your power and vertical speed. If the airplane starts to sink and requires more power, you've probably encountered a headwind to tailwind shear. If you start leveling off and you require less power, you've entered a tailwind to headwind shear. Let's move to a discussion of high altitude weather. I know most of you don't fly at those altitudes, but a few things about the weather there are good to know. The area of the Earth's atmosphere that you and I live in and mostly fly in is called the troposphere. As I mentioned before, the change in temperature as you climb, or lapse rate, is fairly constant in the troposphere. Above that is the stratosphere, where the lapse rate becomes smaller, or the temperature might even increase. The line between the troposphere and stratosphere is called the tropopause, and its height above the ground is determined strictly by the change in the lapse rate. To complicate things a little, there are 3 tropopauses in each hemisphere: the polar, subtropical, and tropical. The trope, as the tropopause is abbreviated, is higher over the equator than over the pole. A typical height might be 55,000 feet over the equator and 25,000 feet over the pole. The 3 tropes don't touch. In the break between them, you'll often find a fast-moving river of air called the jet stream. By definition, the wind must be moving faster than 50 knots to be called a jet stream. The wind in the jet is mostly from the west, and the velocity can reach over 200 knots. This view is from the west, looking in the direction the jet is traveling. You can see the 2 tropes and the break in between. The jet is found in the break. The egg-shaped lines are called isotachs, or lines of equal airspeed. The fastest moving air is in the middle of the jet. The lines are farther apart on the southern end of the jet and closer together on the north. This indicates that there would be less turbulence entering a jet from the south than entering from the north. In fact, the greatest turbulence around the jet stream is found on the northern side, both above and below the core. Jet streams migrate just like ducks and geese. They move south in the winter and north in the summer. Also, the jet increases in velocity and lowers closer to the ground in the winter. That's why you hear a lot of talk in the U.S. about the jet stream during the winter and very little, if any, during the summer. So much for weather theory. Now we know what makes weather work. Now we'll get into our weather dissemination discussion. We're going to talk about how the weather information is sent out to people who need to know, such as pilots. There are various methods of getting the weather out to the pilots. This can be done verbally, through the use of printers, or through the use of charts, or in other words, maps of weather conditions. There are also various methods of collecting the weather. The reports can be made by National Weather Service observers, by FAA observers. Automatic systems or machines can actually measure the weather, and pilots themselves are a good source of actual weather conditions. Now, it's important to check the weather before every flight, IFR and VFR. We can use the weather to determine our proposed altitude, proposed routing, and even the proposed time, because weather might improve as time goes on. So it's important for us to understand the different types of information that we'll be seeing in weather reports and forecasts. There are two basic types of weather reports. The first is called an observation. This is a report of actual weather conditions as they're occurring. The second type of weather report is called a forecast. This is a calculation of weather to exist at a specific time in the future. Now, the first type of report that we'll discuss is the terminal forecast, abbreviated FT in the body of the report. A terminal forecast is for a specific airport and for an area within 5 nautical miles of the runway complex. A terminal forecast is issued 3 times a day, and it's good for 24 hours. An 18-hour forecast and a 6-hour general condition at the end of it, called the categorical outlook. In the regular forecast portion, the letter C stands for ceiling. Cloud heights are in hundreds of feet AGL or above ground level. The visibility is omitted if it's forecast to be above 6 statute miles, and the wind is omitted if it's forecast to be below 6 knots. In the categorical outlook portion, VFR is used for better than 3,000 foot ceiling and 5 miles visibility. Marginal VFR, or MVFR, stands for 1,000 to 3,000 foot ceiling and 3 to 5 miles visibility. IFR stands for 500 to 1,000 foot ceiling and 1 to 3 miles visibility. And low IFR, or LIFR, stands for less than 500 feet or less than 1 mile. The word wind in the categorical outlook forecasts winds of 25 knots or more. Transcribed weather reports, or TWEBs, are forecast weather for a specific route, over 300 of them in the United States. They're given in a route format and are valid for a corridor 25 nautical miles either side of the route. They can be either in a printed form or they are broadcast over certain VORs and NDBs. If a particular nav aid broadcasts TWEBs, then the lower right-hand corner of the station identifier box will have a dark square in it. Or the airport facilities directory will have a dark box by the nav aid info. Area forecasts, abbreviated FA, are printed forecasts for large geographical areas up to several states. It's a single source for forecast frontal movement, turbulence, icing conditions, en route weather, and large weather patterns. They're issued twice a day and are good for 18 hours, a 12-hour forecast, and a 6-hour categorical outlook. The flight precautions section lists IFR conditions, icing, turbulence, mountain obscurations, and thunderstorms. The significant clouds and weather section gives a summary of clouds and weather significant to flight. In this example, the area forecast is good until 2300 Zulu on the 4th of the month. The turbulence sections forecasts occasional moderate turbulence from flight level 250 to flight level 380 due to the jet stream. Turbulence conditions will be moving slowly eastward and continuing beyond 2300 Zulu. The outlook is shown to cover from 2300 Zulu on the 4th until 0500 Zulu on the 5th. For Oklahoma, Arkansas, Texas, Louisiana, Mississippi, and Alabama, and the coastal waters, the forecast is to be 8,000 scattered to clear skies, except the visibility will be below 3 miles due to fog until 1500 Zulu over portions of south central Texas. The outlook after 500 Zulu is expected to be VFR or better than 3,000-foot ceiling and 5 miles visibility. Surface aviation weather reports, also called sequences, are printed reports of actual observed weather. I'd say that I use sequences more often than any other single form of weather report. The observations are made at least hourly while the station is open, or more often if the weather conditions are changing significantly. You'll find 3 abbreviations used on sequences. SA is the usual hourly record. Observations are usually made around 10 minutes before the hour, so the printed reports are transmitted system-wide by 5 or 10 minutes after the hour. SP, for special, refers to an observation made because the weather has changed significantly. RS is a record special, an observation made because the weather changed, but close enough to the normal hourly time to call it the record. Sequences use the standard symbols for cloud cover of SCT for scattered, BKN for broken, CLR for clear, and OVC for overcast. We'll look at a couple examples later on. The letters AMOS, A-M-O-S, found after the station identifier stands for an automatic meteorological observing station. It's a solid-state system capable of automatically observing weather, temperature, dew point, wind direction and speed, altimeter setting, the peak wind speed, and any precipitation accumulation. The sensors are tied directly to the FAA observation network and will transmit a report any time the station is polled by the FAA circuitry. An AMOS station can be manned or unmanned. If it's manned, it can also give cloud height, visibility, and any general remarks. The letters AUTOB, A-U-T-O-B, after the station identifier stands for an automatic observing station. This is basically an upgraded AMOS station. It automatically reports sky conditions, visibility, and precipitation occurrence. It only measures clouds up to 6,000 feet AGL, so it could be clear or overcast above 6,000 feet if clear below 60 is reported. You'll probably be seeing more and more of these, so just be aware that there are some limitations. RADATs, or freezing level data reports, are sometimes added to the end of sequences. They give information on the freezing level and the relative humidity at the freezing level. The wind and temperature aloft forecast, abbreviated FD, is a 12-hour forecast over specific locations at specific altitudes. Some general rules are: the winds aren't listed if within 2,500 feet of the ground, the temperature isn't listed at the 3,000-foot level, winds are listed in true direction and in knots, temperatures are in degrees Celsius and are assumed negative above 24,000 feet. The numbers 9900 mean light and variable winds. There is a method of giving winds that are over 100 knots. They add 50 to the wind direction and give the wind above 100 knots. For example, a wind from 280 at 125 knots would be given as 7825. You add 50 to 280, giving you 78, and subtract 100 from 125, giving you 25. If you saw 8260 in the report, first subtract 50 from 82, giving you 320 degrees true. Then add 100 to the 60, giving you 160 knots. So the wind would be from 320 at 160 knots. If the winds are 199 knots or more, it will only give it as 199 knots. Now the next reports we'll talk about are in-flight advisories. In-flight advisories are unscheduled forecasts of developing hazardous weather. All in-flight advisories use the same location identifiers. So you should learn the particular location identifiers around you so that you can easily determine whether a particular in-flight advisory would be of significance to you. There are three types of in-flight advisories: airmets, sigmets, and convective sigmets. An airmet is hazardous weather for light aircraft and VFR pilots. Within an airmet, you'll find moderate icing conditions, moderate turbulence, and sustained winds of 30 knots or more. Sigmets cover weather that's hazardous to all aircraft, such as severe icing, severe or greater turbulence, dust storms, sandstorms, or volcanic ash. Convective sigmets are issued for thunderstorm activity and are also for all aircraft. All in-flight advisories are broadcast when they first are issued by the flight service station and are referred to by air traffic control. If you ever miss the broadcast, call the local flight service station for the report. Pilot weather reports, called PIREPs, are reports of actual weather conditions given by a pilot in flight to air traffic control or the flight service station. They're abbreviated UA in the body of the report and are your best source for actual cloud cover, icing, and turbulence.
Center, this is Archer 02 Lima, level at 8,000 feet, experiencing light to moderate chop, sir. And we are having slight difficulty holding our altitude.
While you're in flight, there is a service that's available for you to find out the latest weather conditions, forecasts, and weather reports, even after you've left your departure point. This is the En route Flight Advisory Service, EFAS. It's also called FlightWatch. Now, FlightWatch is part of the flight service station, and it uses a common radio frequency of 122.0. The FlightWatch specialist keeps track of the developing weather and the latest weather conditions. You should only use FlightWatch when you're above 5,000 feet AGL, since this way you're assured that you have radio contact. If you want to talk with FlightWatch, just dial up 122.0, call FlightWatch, state your call sign, and your position. The closest FlightWatch station will get back to you, and after he does, just ask for whatever information you're looking for. Once you get the information that you desire, be sure to give him a PIREP or a pilot report, even if it's beautiful weather, clear, no turbulence. Now we'll move on to the convective outlook. The convective outlook report, labeled AC, describes the prospect for general and severe thunderstorm activity during the following 24 hours. So it's a forecast rather than an observation. The outlook is transmitted over the printer and is fairly self-explanatory. The hardest part for me is making sense out of the abbreviations. For an example, upper level low near some identifier MLI with a trough extending southward into eastern Texas, expecting to move northeastward. Now let's look at weather reports that are given in chart or map form. The first one we'll talk about is the high-level significant weather prognostic chart. Anytime you see the term prognostic, abbreviated PROG, mean that it's a forecast in chart form. This PROG covers airspace from 24,000 to 63,000 feet pressure altitude. It shows area of turbulence, areas of expected cumulonimbus development, and the location and strength of the jet stream, and the height of the tropopause. The symbol CB for cumulonimbus implies hail, moderate or greater turbulence, and icing. Forecasted turbulence is enclosed by the dashed lines. One top hat is used for moderate turbulence and two top hats for severe. The altitude of the forecasted turbulence is shown as the two numbers separated by the line, the top of the forecast above the line and the bottom below the line. Forecasted CBs are enclosed by the scalloped lines with height symbols the same as with turbulence. The trope height is shown in the boxes in hundreds of feet, and the jet stream speed is shown using the flags. Each flag is 50 knots, and each line is 10 knots. The weather depiction chart is computer prepared from sequences to give a broad overview of observed weather conditions. It's really a good place to begin a weather briefing because it gives a general overview of the actual weather as of the valid time on the chart. The legend on the chart indicates what the shading and contoured areas show. Shaded areas are IFR, or less than 1003, and the contoured areas are marginal VFR, or ceiling from 1,000 to 3,000 feet, and visibility from 3 to 5 miles. The little circles show the cloud cover at each station. Open circle is for clear skies. Scattered clouds are shown as a quarter blocked in. Broken is 3/4 colored, and overcast as a black circle. The low-level significant weather prog chart is made up of 4 panels. The 2 lower panels are 12 and 24-hour surface progs. The 2 upper panels are 12 and 24-hour progs from the surface to 400 millibars, or 24,000 feet. The charts show conditions as they're forecast to be at the valid time of the chart shown on the panel. You should use the top and bottom panels together to get an overall picture of the weather conditions over a certain area. Between the top 2 panels is a legend which describes how the chart depicts IFR, marginal VFR, turbulence, and the freezing level. The areas enclosed by dots and dashes are covered by showery precipitation, while the areas enclosed by a solid line have continuous precipitation. Shaded areas cover half or more of the area, while unshaded are less than half. Radar weather reports are in printed form and describe thunderstorms and general areas of precipitation as discovered by radar. I've included it in the chart section because we'll next see a chart compiled from all the radar weather reports. The report includes a location of precipitation along with a type, intensity, and trend. The radar summary chart graphically displays the collection of radar weather reports. The computer-generated chart is valid at the time of the plotted radar reports. Remember, the chart shows radar echoes, not cloud heights. NE stands for no echo. The legend at the bottom says that movement of areas and lines are shown with pennants, while movement of individual cells is shown by the arrows with the speed. There are 3 levels of contour lines, each level indicating more intense storms. A line of echoes is shown by the dark, heavy line on the chart. We've covered a lot in this weather section, both weather theory and weather dissemination. And there's a lot more we could cover, but these are just the basics that you need to know to pass your FAA exam. In the future, you should find the FAA texts available that very thoroughly cover all aspects of weather, and I would suggest that you do that. Also, just in your future flying, you're going to find that the more you use the weather charts and weather forecasts, the more familiar and second nature they're going to become.
Okay, let's start with some FAA questions. These are the identical, verbatim questions and answers that you're going to see on the real test. This is a chance to see what you just learned in the weather theory module. We're going to start with question number 764 on page 63. You can either open your book and follow along or follow on the television set. You're going to get a chance to work all these questions again with the sample exams we want you to do at the end of the course. Question 764. Ceiling, as used in aviation weather reports, is defined as the height above the Earth's surface of the...
It's answer 2, lowest layer of clouds reported as broken or overcast and not classified as thin.
Okay, question 765. What feature is associated with a temperature inversion?
Well, remember, a temperature inversion has warm air over cold air, just opposite of normal. So you're going to need stable air to allow this to occur. It's answer 1, a stable layer of air.
Question 766. The most frequent type of ground or surface-based temperature inversion is that produced by?
Answer 1, terrestrial radiation on a clear, relatively still night.
Question 767. A temperature inversion would most likely result in which weather condition?
Answer 3, an increase in temperature as altitude is increased.
Question 768. Which weather conditions should be expected beneath a low-level temperature inversion layer when the relative humidity is high?
Well, the inversion is going to trap anything, any impurities or smoke or haze within, just like as if you put a lid over a boiling pot. So it's answer 1, smooth air and poor visibility due to fog, haze, or low clouds.
This is the kind of conditions we get in Denver, Colorado, and Los Angeles. Wherever there's a valley, this is real common. It traps all the pollutants and the smog, and humidity is what really makes it up. It gives you that condensation nuclei for the stuff to attach to. Question 769. Every physical process of weather is accompanied by or is a result of?
Answer 3, a heat exchange.
Let's go on to next page, 770. What causes variations in altimeter settings between weather reporting points?
It's answer 1, unequal heating of the Earth's surface.
Question 771. What are the standard temperature and pressure values for sea level?
Well, for sea level, for temperature, it's 15 degrees Celsius, remember, or 59 degrees Fahrenheit, and 29.92 inches of mercury. And the answer is 1, 15 degrees C for Celsius, and 29.92 inches of mercury.
Question 772. Winds at 5,000 feet AGL, AGL means above ground level, on a particular flight are southwesterly, while most of the surface winds are southerly. This difference in direction is primarily due to?
The answer is number 2, friction between the wind and the surface.
Question 774. If the temperature dew point spread is small and decreasing, and the temperature is 62 degrees Fahrenheit, what type weather is most likely to develop?
Remember, the dew point, temperature dew point spread is the difference between the actual temperature or the ambient temperature and the dew point. So if the spread is small, that means they're close together or you're very humid. So the answer is number 3, fog or low clouds.
Question 775. What is meant by the term dew point?
Number 3, the temperature to which air must be cooled to become saturated.
776. The amount of water vapor which the air can hold largely depends on?
Number 2, the air temperature.
Question 777. What are the processes by which moisture is added to unsaturated air?
Answer 2, evaporation and sublimation.
778. The presence of ice pellets at the surface is evidence that?
Well, it tells us a couple of things. Ice pellets, remember, are frozen, freezing rain. So it tells us, first of all, that you have freezing rain above you, and also it tells you that you have above freezing temperatures above the freezing rain. So the answer is 3, there is freezing rain at a higher altitude.
Jeff, this is the first time I've seen this question on the private pilot exam. Could we tell the difference between ice pellets and hail at the surface?
Well, hail is a lot larger, Steve. Ice pellets are really small. They sometimes call that corn snow. I've heard it called corn snow. It's really small, about the size of BBs, something like that. And hail typically is much larger and like a mixture of cloudy and clear, where the ice pellets are white, almost like they're painted white.
Thanks. Question 779. Clouds, fog, or dew will always form when?
Number 1, when water vapor condenses.
Question 780. Which of the following measurements can be used to determine the stability of the atmosphere?
The answer is number 2, the actual lapse rate.
Question 781. Which of the following would decrease the stability of an air mass?
Well, the answer is number 1, warming from below, and it's interesting that that's in fact what normally occurs on the Earth's surface. Of course, the sun's rays strike the Earth and warm the air above it, and you can see that this whole thing is like a boiling pot, whereas a pond, the sun rays hit the water and the top layer of the water in a body of water and warm that upper layer, and the bottom layers stay cool. So that's a body of water is typically very stable, whereas our atmosphere is very unstable.
Thanks, Jeff. Question 782. The conditions necessary for the formation of cumulonimbus clouds are a lifting action and...
You need three things. You need lifting action, some sort of instability, and high relative humidity at all flight levels. So it's answer 2, unstable, moist air.
Question 783. What is the characteristic of stable air?
Well, if we remember from our curriculum, the whole list of all of the characteristics of stable air, one of them is stratiform, or these sheet-like clouds. That's answer number 1, stratiform clouds.
Question 784. Moist, stable air flowing upslope can be expected to...
Answer 1, produce stratus-type clouds.
Question 785. If an unstable air mass is forced upward, what type clouds can be expected?
Answer 4, clouds with considerable vertical development and associated turbulence.
Question 786. What is the approximate base of the cumulus clouds if the temperature at 1,000 feet MSL is 70 degrees Fahrenheit and the dew point is 48?
Well, remember for our curriculum, we take the difference between the temperature and the dew point, and then we divide that by 4.4, and that will give us the height of cumulus clouds in hundreds of feet. They tell you that the temperature at 1,000 feet MSL is 70 degrees and the dew point's 48. So 70 minus 48 is 22. And if you divide 22 by 4.4, you come up with 5. Well, that means it'd be 5,000 feet above where that was measured, and it was measured at 1,000 feet MSL, so at 6,000 feet, and that's answer number 3.
I don't know how he keeps all that information in his head. Question number 787. At approximately what altitude above the surface would the pilot expect the base of cumuliform clouds if the surface air temperature is 82 degrees Fahrenheit and the dew point is 38?
Well, 82 minus 38, the temperature minus the dew point, is 44 degrees. You divide that by 4.4, comes up with 10. So you can expect the bases of the clouds at that area to be at 10,000 feet. It's answer 3, 10,000 feet AGL, above ground level.
Question 789. The suffix nimbus used in naming clouds means?
Number 2, a rain cloud.
Question 790. An almond or a lens-shaped cloud which appears stationary but which may contain winds of 50 knots or more is referred to as?
Answer number 3, a lenticular cloud.
They call it lenticular because it's lens-shaped. That's a pretty easy way to remember that one, and I don't think there's any other answers that would suck you in if you can remember lens and lenticular. Question 791. Clouds are divided into 4 families according to their?
According to their height range, answer number 3.
Question 792. Which clouds have the greatest turbulence?
Well, it's answer 2, the cumulonimbus, CBs or thunderstorms.
Question 793. Which cloud types would indicate convective turbulence?
Answer 3, towering cumulus clouds.
794. A moist, unstable air mass is characterized by?
Okay, we have unstable air in this case, so you're going to have our puffy type clouds, the cumuliform type clouds. So it's answer 1, cumuliform clouds and showery precipitation.
795. What are characteristics of unstable air?
Unstable air will give you turbulence, and because of this turbulence, the visibility will normally be good except in blowing obstructions or rain showers. So it's answer 1, turbulence and good surface visibility.
796. A stable air mass is most likely to have which characteristics?
Stable, smooth, so it's answer 3, smooth air.
797. An unstable air mass is most likely to have which characteristics?
Well, just the opposite. Answer 2, turbulent air.
798. One weather phenomenon which will always occur when flying across a front is?
Answer 1, a change in the wind.
Question 799. One of the most easily recognized discontinuities across a front is?
Answer 2, the wind.
Let's turn the page, go to the next question, 800. Steady precipitation, in contrast to showery activity preceding a front, is an indication of.
Answer 4, stratiform clouds with little or no turbulence.
801. What is indicated when a current SIGMET forecasts embedded thunderstorms?
Remember, a SIGMET is applicable to all aircraft. AirMets are just to smaller aircraft. So when they talk about embedded thunderstorms, what they're really asking in this question is just what's the definition of embedded thunderstorms? That's answer 4. Thunderstorms are obscured by massive cloud layers and cannot be seen.
If you have any trouble remembering the difference between an AirMet or a SIGMET, AirMet are for airmen, which is what we are flying small planes. SIGMETs are significant and affect all aircraft. Question 802. Crests of standing mountain waves may be marked by stationary lens-shaped clouds known as.
Well, they're called standing lenticulars. Answer number 2, standing lenticular clouds.
Lens-shaped lenticular. Just remember that. Question 803. Hazardous wind shear is commonly encountered near the ground.
Answer 3, during periods of strong temperature inversion and near thunderstorms.
You can see that we're not giving you big detailed explanations of every question. We've covered all the subjects in the curriculum and are using this to reinforce your knowledge. We're also not covering all the wrong answers for 2 reasons. There's not enough time in the course to do it. We want you to hear, and we want this to click the right answer. That's why we're covering the right ones, and only a few times in the course pick apart wrong ones to show you some examples. Question number 804. Possible mountain wave turbulence would be anticipated when winds of.
This question might be for glider. Of course, the FAA doesn't let us know that, but in doing my research, I really feel that it's going to be a glider question, but we want to give it to you anyway in case it's not. It's answer 2, 40 knots or greater blow across a mountain ridge and the air is stable.
Question 805. A pilot can expect a wind shear zone in a temperature inversion whenever the wind speed at 2,000 feet to 4,000 feet above the surface is at least.
Answer 4, at least 25 knots.
806. One in-flight condition necessary for structural icing to form is.
Well, this is asking about structural icing as opposed to carburetor icing. So for structural icing, icing on the wings or whatever, you need visible moisture. Answer 4.
Question 807. In which environment is aircraft structural ice most likely to have the highest accumulation rate?
That's the danger behind freezing rain, remember, is you have the highest accumulation of structural ice. So it's answer 4 for freezing rain.
I'm sure you've seen on television that, especially involving accidents, and airplanes have accidents like cars and anything else that we're involved with as people, that the one threat to
heavy or severe freezing rain, you just stay away from it. I mean, nobody goes near it.
you don't take off.
Well, or land, wherever it is, yeah.
Okay, thanks. Question 808. What is frost considered hazardous to flight?
That's answer 4. Frost causes early airflow separation, resulting in the loss of lift.
Which means you want to take frost off before you go flying. A little bit of frost can form on fuel tanks when you're descending from a high altitude that's cold down to a lower altitude where there's warm and more moisture. That doesn't pose any problem to flight. What the FAA really wants you to know is never take off with frost on your wings. There have been numerous accidents. And when I was a pilot in Alaska, I personally saw airplanes pile up at the end of the runway trying to take off with frost. So that can be avoided. Question
809.
809. Which conditions result in the formation of frost?
Well, it's answer 3. The temperature of the collecting surface is at or below the dew point of the adjacent air, and the dew point is below freezing.
That's the example I just gave about descending from a cooler area to a warmer area. Question 810. Frost, which has not been removed from the lifting surfaces of an airplane before flight.
Number 1, may prevent the airplane from becoming airborne.
Question 811. What feature is normally associated with cumulus stage of a thunderstorm?
Remember, the cumulus stage is the second of the 3 stages. We have the building stage, or I should say the first of the 3 stages. We have the cumulus stage, which is the building stage. Then we have the mature stage, which has both updrafts and downdrafts. And then we have the dissipating stage, and that's when we get the anvil. So it's continuous updraft.
Question 812. Which weather phenomenon signals the beginning of the mature stage of a thunderstorm?
Answer 2, precipitation is beginning to fall.
Question 813. Thunderstorms, which generally produce the most intense hazard to aircraft, are?
Well, the worst type thunderstorms are squall-like thunderstorms. That's not to say that regular garden variety plain vanilla thunderstorms aren't dangerous. They are, certainly to light aircraft. But the most severe type thunderstorms, the one that give you the huge hail, 2 or 3 inch hail, tornadoes and gusting winds of over 50 knots, those type thunderstorms typically come from squall lines. That's answer number 4.
What's happening is cold air is getting under warm air and pushing it up at a rapid rate, and you have the most unstable condition we could possibly get. The question 814, what conditions are necessary for the formation of thunderstorms?
Need 3 things, and it's answer 1, a lifting force, high humidity, and unstable conditions.
Question 815, during the life cycle of a thunderstorm, which stage is characterized predominantly by downdrafts?
Well, this is the last stage of the thunderstorm. It's answer 2, dissipating.
816, thunderstorms reach their greatest intensity during the...
Number 2, during the mature stage, and that's because you have both updrafts and downdrafts, and that's where you get the highest amount of turbulence, and those are the ones you really want to stay away from.
You want to stay away from all of them, and don't ever try to fly in one. The FAA says you should maintain a distance of 20 miles. If you're behind one, I don't know if you need to quite stay that far behind, but if you ever find yourself in one or think you're in one, don't turn around. You want to go straight through for 2 reasons. It's probably the shortest way out, and there's less damage to your aircraft from hail damage if you don't make a turn. Question number 817, which weather phenomenon is always associated with a thunderstorm?
Well, it's answer 1, lightning.
818, if there is a thunderstorm activity in the vicinity of an airport at which you plan to land, which hazardous and invisible atmospheric phenomenon might be expected on the landing approach?
Answer 2, wind shear turbulence.
Question 819, a non-frontal, narrow band of active thunderstorms that often develop ahead of a cold front is known as...
Number 3, that's the definition of a squall line.
Upon encountering severe turbulence, which conditions should the pilot attempt to maintain?
If you get into severe turbulence, and if you, by reading the FAA's own description of the different classifications of turbulence, severe turbulence is that the aircraft is uncontrollable. So if you get into severe turbulence, you don't try to maintain your altitude and you don't try to maintain your airspeed. What you maintain is a level flight attitude. So it's answer number 3, level flight attitude.
I can guarantee you that in severe turbulence in a little Cessna or a little Piper, your airspeed will vary all the way from stall into the yellow arc. And all you can do is maintain a level flight attitude or attempt to. If you tried to chase the airspeed indicator, you wouldn't be up there for 5 seconds. Question 821, what situation is most conducive to the formation of radiation fog?
Answer 1, warm, moist air over low flatland areas on clear, calm nights.
Question 822, low-level turbulence can occur and icing can become hazardous in...
The answer is number 4, steam fog, and I need to mention what steam fog actually is. They sometimes call this sea smoke. It's the same sort of thing that you see coming off of a steaming cup of coffee. That's what we're talking about when we say steam fog. And all that is when you have cold air over warmer, moist, a warm, moist body of water. Of course, a body of water would be moist, but warmer. And you see this a lot in the Great Lakes section of the United States during the winter. And the 2 dangers about sea smoke or steam fog are turbulence and a tremendous accumulation of ice if you happen to be caught in it. So you want to climb above that and don't go through steam fog.
You're not allowed in any type of fog until you're instrument rated anyways. So question 823, in which situation is advection fog most likely to form?
Answer 2, an air mass moving inland from the coast in winter.
Next question is 828 on page 68. To best determine forecast weather conditions between weather reporting stations, the pilot should refer to...
Answer 4, area forecasts.
Question 829. To determine the freezing level and areas of probable icing aloft, the pilot should refer to...
Again, the answer is area forecasts, choice 3.
Question 830. To obtain a continuous transcribed weather briefing, including winds aloft and route forecasts for a cross-country flight, a pilot should monitor...
Well, there's 3 words in this question that give us the answer. The first is transcribed, and the last 2 are route forecasts. So anytime you see that in a body of a question, what you're looking for is a TWEB, a TWEB, and that's answer 1 on a low-frequency radio receiver.
831. Individual forecasts for specific routes of flight can be obtained from which weather service?
Again, we're talking about a route, and so it's a transcribed weather broadcast. Answer 1.
One more question on this, 832. TWEBs, or transcribed weather broadcasts, may be monitored by tuning the appropriate radio receiver to certain.
Number 3, VOR and NDB frequencies.
833. To get a complete weather briefing for the planned flight, the pilot should request.
Answer 4, a standard briefing.
834. Which type of briefing should a pilot request to supplement mass disseminated data?
That's answer 3. That's an abbreviated briefing.
Question 835. A weather briefing that is provided when the information requested is 6 or more hours in advance of the proposed departure time is?
Answer number 1, an outlook briefing.
836. SIGMETs are issued as a warning of weather conditions hazardous.
Number 2, to all aircraft.
And AirMets, which we remember are for airmen, are issued as a warning of weather conditions hazardous.
Answer 2, particularly to light aircraft.
838. Which in-flight advisory would contain information on severe icing?
Well, severe icing is going to be a big deal to any pilot and any type of aircraft, whether or not he's a light aircraft or a large airliner. So it's answer 1, answer 2, a SIGMET.
839. What information is contained in a convective SIGMET in the conterminous United States?
Convective SIGMETs have to do with convective activity like thunderstorms. It's answer 1, tornadoes, embedded thunderstorms, and hail 3/4 of an inch or greater in diameter.
840. What information is provided by radar summary chart that is not shown on other weather charts?
It's answer 1, lines and cells of hazardous thunderstorms.
841. What values are used for winds aloft forecasts?
Remember, you're always going to have the winds reported to you at altitude in true direction and in knots. The only time winds are reported in magnetic direction are when they come from the tower or ground control talking about the winds at that particular airport. So it's answer number 3, true direction and knots.
842. The section of the area forecast entitled Significant Clouds and Weather contains a...
Answer number 1, a summary of cloudiness and weather significant to flight operations broken down by states or other geographical areas.
843. Radar weather reports are of special interest to pilots because they indicate...
Answer 2, the location of precipitation along with the type, intensity, and trend.
844. From which primary source should information be obtained regarding expected weather at the estimated time of arrival at your destination?
We're talking about at your destination and expected weather, so a forecast. So what we're looking for then is a terminal forecast, answer number 3.
Now we'll look at some weather reports and forecasts, starting with question number 845. What hazards are forecast in the area forecast, figure 50, for Tennessee, Alabama, and the coastal waters?
Well, looking at our area forecast, figure 50, we see an area here that talks about Tennessee, Alabama, and the coastal waters. So we know we're in the right section for answering this particular question. And a couple lines in, it says occasional moderate turbulence, 250, that's 25,000 feet, to 380, 38,000 feet, due to the jet stream. So that answer is found in number 4, moderate turbulence from 25,000 to 38,000 feet due to the jet stream.
Question 846. What type of obstructions to vision, if any, are forecast for the entire area from 2300 Zulu until 0500 Zulu the next day?
Again, referring to figure 50, we need to find that time group from 2300 Zulu to 0500 Zulu. And down on the bottom, we'll see a time group right here where it says 04. That means just the date on the 4th of the month. From 2300 to on the 05, the 5th of the month, at 0500, that is the categorical outlook where it says outlook. So we're looking for something in the body then down here that has outlook, and we see right here it says outlook VFR, also outlook VFR. So it's answer 1, none of any significance. VFR is forecast.
Question 847. What sky condition and type obstructions to vision, if any, are forecast for all the area except Tennessee from 1040 Zulu until 2300 Zulu?
Well, in the bottom part of the area forecast, we can see for all of these states, Oklahoma, Arkansas, Texas, Louisiana, Mississippi, Alabama, and coastal waters, we have a forecast. And then only for Tennessee, we have another forecast. So they're asking about for all of these states except Tennessee, and it says 8,000 scattered to clear except visibility below 3 miles due to fog. So it's answer number 3, 8,000 feet scattered to clear except visibility below 3 miles in fog until 15Z over south central Texas.
Question 848. The forecast ceiling and visibility for the entire area in figure 50 from 2300Z through 0500Z is ceiling.
Well, we've already spoken that time period from 2300 to 0500 is that the tail end of our area forecast, or the excuse me, the categorical outlook. So again, we need to look under the area forecast to find categorical outlook, and it's the same place for a previous problem where it says outlook VFR. To answer the question, though, we have to realize that VFR is not the VFR you think of when you say you're flying VFR. It's not 1003. For these charts, VFR is weather better than 3,000 foot ceiling and 5 miles visibility. So it's answer 4, greater than 3,000 feet and visibility greater than 5 statute miles.
849. We'll refer now to figure 51. What wind is forecast for St. Louis at 18,000 feet?
Well, we'll refer to figure 1 and that 51, and that is a winds and temperatures aloft forecast. We find St. Louis, which is on the bottom row, and we find they're asking about 18,000 feet. So we find the 18,000 feet column and read down, and this is the block that we have here, 2356 minus 16. The winds are from 230 true at 56 knots, and the temperature is forecast to be minus 16 degrees Celsius. So it would be answer number 3, 230 at 56 knots.
Question 850. Determine the wind and temperature aloft forecast for Denver at 30,000 feet.
Well, again, on the winds and temperature aloft, we find the row for Denver, which is about midway, and then 30,000 feet, and read down and find the block. And the block that we see now is 235347. We need to remember now that the temperatures are assumed negative, if it says, as it says at the top of the chart here, are assumed negative above 24,000. We're at 30, so that temperature is actually minus 47, and the winds would be from 230 at 53 knots. So it's answer number 2, 230 at 53 knots, and the temperature is minus 47 degrees Celsius.
You know, I'm not sure why the FAA even wants you to understand that, because you're not allowed to fly above 18,000 feet until you're instrument rated. But let's move on to question 851. Interpret the wind and temperature aloft forecast for 3,000 feet at Kansas City.
Well, again, we refer to figure 51 and find Kansas City. That is actually, MKC is Kansas City downtown, and then 3,000 feet, the block is 050 at 7 knots. So the answer is number 1, 050 at 7 knots, and the temperature is missing.
Question 852. When the term light and variable is used in reference to a winds and temperature aloft forecast, the coded group and wind speed is?
Remember, light and variable is 9900. If you ever see that's what it means. It's answer 3, 9900 and less than 5 knots.
853. What wind is forecast for St. Louis STL at 34,000 feet?
Well, again, St. Louis is on the bottom part of the bottom row of figure 51. We find under 34,000 feet the column 730649. Well, 73 is a direction, and that's more than 360 degrees. So this is the code telling us that we have a wind speed greater than 100 knots. We subtract 50 from 73, giving us 23. So the winds are from 230, and we add 100 to the next two numbers, 06. So the winds are at 106 knots, and the temperature would be minus 49. It's answer number 4, 230 at 106 knots.
If for some reason you didn't remember that little formula Jeff just went by, you can look at the other 3 answers and see that none of them end in a 10-degree increment, which would make them wrong anyways. Even though 4 might be a stumper, you might say, oh, are the winds ever 106 knots? 34,000 feet, that happens all the time. Question 854. What are the current conditions depicted for Chicago Midway Airport in figure 52 It's got the designator MDW.
First of all, Figure 52 is a compilation or a list about 5 separate sequences, aviation weather reports, and these are the sequences or the actual hourly reports. And let's see what the weather says, and we'll just read what it says for Midway. MDW, which is Midway, RS means it's a record special. At 1856 Zulu, we have partial obscuration, minus X is partial obscuration, measured 700 feet overcast, OVC is overcast. The visibility is not 11, it's 1 1/2 with rain, and the plus after the R means it's heavy rain and fog. The altimeter, sea level altimeter, or the altimeter corrected to sea level in millibars is 10, I guess it would be 999.0. You don't need to use it, you never use millibars. Obviously, I don't use it that often. Temperature is 63 degrees Fahrenheit. The dew point is 61 degrees Fahrenheit. The winds are from 320 at 5 knots. The altimeter is 2980. It's either it's right around 300. It wouldn't be, obviously would not be 3980, so you put a 2 in front of this one, 2980. Then you have RF2, RB12. Rain and fog covered, obscured 2/10 of the sky, and the rain began at 12 after the hour. Now the report was 1856, so the rain began at 1812. So we'll look for an answer that has something like that. The sky is partially obscured, measured ceiling 700 feet overcast, visibility 1 1/2 with heavy rain and fog.
Answer number 2. 855. Which of the reporting stations in Figure 52 have VFR weather?
Well, let's look again at Figure 52, and we'll just read all of these sequences to give you a little experience in reading them. INK, wink, SA, it's an hourly, it's a sequence. At 1854 Zulu, clear, 15 miles visibility. That's again the altimeter in millibars. That would be 1010.6. Temperature 77, dew point 63. The winds are 110 at 12. G is gusting to 18 knots, and the altimeter with 3 zeros, that would be 3000. So that's wink. Next we'll look at the next one, which is Boise. Again an hourly sequence at 1854 Zulu. 15,000 scattered. You had 2 zeros. 15,000 scattered with 30 miles visibility. The altimeter in millibars, I won't even talk about that. 62 degrees is the temperature, 42 is the dew point. The winds are from 130 at 4 knots, and the altimeter is 3015. Los Angeles International, LAX, again hourly record or hourly sequence, 1852, 700 feet scattered, 25,000 feet scattered, 6 miles, and you have haze, that's H, and smoke, that's K. S is not smoke, S is snow. So it's 6 miles due to haze and smoke, or what they call smog. Temperature is 60 degrees, dew point 59. The winds are from 250 at 4 knots, and the altimeter is 29.91. We've already talked about Midway, so we'll go down to JFK, which is Kennedy Airport in New York City. It's a record special at 1853 Zulu. We have indefinite ceiling. That W stands for indefinite ceiling. You're just going to have to memorize that. 500 feet obscured, X is obscured, 1/2 mile visibility due to fog. The temperature is 68, the dew point is 64. The winds are 180, from 180 at 4 knots. The altimeter is 30.06 inches of mercury. And then we have a remark that talks about the visibility. They're just saying runway 04 RVR, runway visual range, is 2,200, variable to 3,000 feet. And then tower visibility is a 1/4 mile. So looking at these, then we can see that JFK has less than VFR weather. It's 500 obscured, and Midway is partially obscured, 700 overcast. So those two do not have VFR weather. Those are IFR weather, and the other 3 have VFR weather. So to answer question 855, it's answer 3, all except JFK and Midway.
856, the wind direction and velocity at JFK is from?
I'm not going to go back to that chart. I've already read it. You can refer to it if you don't recall, but it's answer 3, 180 at 4 knots.
Question 857, what are the wind conditions at Wink, Texas?
Answer 4, out of 110 degrees at 12 knots, gusting to 18 knots.
858. In Figure 52, the remarks section for MDW, or Midway, has RF2 and RB12 listed. These two entries mean?
Remember, RF2 has to do with rain and fog obscuring 2/10 of the sky, and RB12 has to do with the rain began at 12 after the hour. Well, to know the exact time, you need to go back to the left to find out the time of the report at 1856. If the report was made at 1856, obviously the rain did not begin at 1912. It began at 1812. So it would be answer number 3. Rain and fog are obscuring 2/10 of the sky, and rain began at 1812 Zulu.
859. According to the terminal forecast for Oklahoma City, OKC, Figure 53, the cold front should pass through.
We're going to look at several terminal forecasts for Figure 53, and under Oklahoma City, what we want to find are the letters CFP for cold front passage, since that's what they ask for in the question. When you refer to Figure 53 under Oklahoma City out here at OKC, we can see right here that we have the letters CFP, and they follow the time of 21 Zulu. So you read this, it says by 21 Zulu, you're going to have cold front passage. So we want to find the answer that says that. That's answer 2, by 21Z.
860. What wind conditions are expected at Hobart, HBR, at 1600 Zulu?
Let's look at Hobart, HBR, and find the terminal forecast here. And it says at or 16 Zulus. We see the time group that covers 16 Zulu. Here's one that starts at 17 Zulu, so the 16 Zulu is going to be before that. And it says ceiling of 12,000 broken, 25,000 broken, and the winds are 300 at 10 knots. So that's answer number 3, 300 at 10 knots.
861. What ceiling is forecast for gauge, GAG, between 16Z and midnight Zulu?
Well, we find GAG, or gauge, on the terminal forecast and read over until we find a time that fits in that 16 Zulu. When we do that, we see the period. That means that's the end of the forecast for that time. And then by 16 Zulu, here we have another forecast, and we're having forecast to have 6,000 feet scattered, a ceiling of 10,000 feet broken. The winds from 330 at 15 knots, gusting to 22 knots. So it's answer number 4, 10,000 feet broken.
Question 862. What is the outlook for weather conditions at McAllister, MLC?
Well, the outlook, remember, on a terminal forecast or an area forecast is the last part of the forecast. And so we want to look at the very end of that portion for McAllister, Oklahoma. And that's found in the last line of McAllister, where it says by 09Z you should have marginal VFR due to ceiling and thunderstorms and rain showers. T is thunderstorms, RW is rain showers. So it's answer number 4, marginal VFR due to low ceilings and thunder showers.
863, the wind condition in the terminal forecast outlook for Ponca City, PNC, is?
Again, they're asking about the categorical outlook, the outlook portion, so that's the very last portion of the terminal forecast for Ponca City. Looking at Ponca City in the last line where it says by 09 Zulu, you should be VFR and wind. And the wind, remember, is telling you that you're going to have winds of 25 knots or more, so it's answer 2 for velocities of 25 knots or stronger.
864, when is the wind forecast to shift at Tulsa, TUL?
Let's look at what it says for Tulsa in the terminal forecast, and we can see that at 15 Zulu, the winds are forecast to be 190, or basically out of the south. By 19 Zulu, the winds are forecast to be from 180, again, basically out of the south. Then by 23 Zulu, we're going to have cold front passage. So that's telling us that's usually, remember, when you go through a cold or a front, whether it's a warm front or cold front, you're going to have a shift in winds. So that's probably when it is going to occur, and that's going to be found down on the next line where it says the winds are now forecast by 23 Zulu to be from 320 at 15, gusting to 225. So the winds until then were out of the south, and then by 23 Zulu, they were supposed to be out of the northwest. So it's answer number 2 by 23Z.
Next page, 865. Of what value is the depiction chart in figure 54 to the pilot?
Well, let's look at figure 54 and just see what a weather depiction chart is, and you can see that it just gives you an idea of the weather. We have VFR and IFR shown. IFR is this shaded area, VFR is the clear area, and then within the solid line out here, that's marginal VFR. You also have fronts shown and ceilings. We'll show you some things in some following problems that pick this apart a little bit, but the answer to that question is number one, to determine general weather conditions on which to base flight planning.
866. The IFR weather in eastern Texas in figure 54 is due to.
Well, remember, IFR weather is that shaded or cross-hatched area, so we need to find the IFR in eastern Texas, and that is over here on the border with Louisiana, the shaded area, and we can see just to the left here. You might not be able to see it too well on your television, but if you pull out the chart, figure 54 in the back, you can see it. Two little, like an equal sign, two little dashes, and that equal sign stands for fog, so it's answer number 2, fog.
867. What weather phenomenon is causing IFR conditions along the coast of Oregon and California?
Again, we need to find a shaded area along the coast of Oregon and California and see what it says for obstructions division. And right here we see it's like quote sign, two little commas, two little quotes. That stands for drizzle. So it's answer number 4, drizzle.
868. What is the status of the front that extends from New Mexico to Indiana is depicted in figure 54?
We'll find a line that shows us the front, and it starts in New Mexico here, where we have a sharp barb on one side and the rounded barb on the other side, and that, remember, is a stationary front. So we can see all the way up here, it's the teeth on one side and the balloon on the other side, so it's a stationary front. That's answer number 1, stationary.
869. According to the depiction chart in figure 54, the current weather for a flight from central Arkansas to southeast Alabama is?
Well, for Arkansas, we can see central Arkansas here. We have a circle with about 3/4 of it is blacked in. That's broken clouds, and the ceiling is 25,000 feet. Through Mississippi, we have a 1/4 blacked in circle. That's scattered. Here's a 3/4 circle, that's broken, and both have 250, indicating a ceiling of 25,000 feet. And in Alabama, southeastern Alabama, we have again 1/4 blackened in, that is scattered clouds, 25,000-foot ceiling, so it's answer number 3, broken to scattered clouds at 25,000 feet.
870 is next. What weather is forecast for the Gulf Coast area just ahead of the cold front during the first 12 hours?
Let's look at figure, what is this, figure 55 in the back of the book. And remember now that these 4 panels, these 2 are from the 12-hour forecasts. And you can read just off to the left what it actually is. This is 12-hour significant weather Prague, low level, surface to 400 millibars. And then we go down to the one below it. It says that that's a surface Prague, or remember Prague is a forecast, and 12 hours. So that these, the 2 left charts, are 12-hour, and the 2 on the right are 24-hour surface Pragues. They're asking about the first 12 hours, so we're talking about these 2 charts on the left. And notice on the left that we have on our surface Prague that, I'm sorry, on the low-level Prague, that we have the ceiling is, you see this scalloped edge here, that we have marginal VFR weather to IFR weather within this straight line. So that is found on the upper one. For the lower one, then, we look down to what is possibly causing this marginal VFR to IFR weather. And if you look really closely, we see our thunderstorm symbol and our rain shower symbol. So it's answer number 1, marginal VFR to IFR with intermittent thunder showers and rain showers.
Question 871. For what phase of flight planning are the significant weather Pragues designed?
Let's answer 2, information to avoid areas and or altitudes of the freezing level and turbulence.
872. Interpret the weather symbol depicted in Lower California on the 12-hour significant weather Prague in figure 55.
Well, the 12-hour significant weather prog, remember, is the upper right-hand panel of figure 55. And when you look in there in Southern California, we see our dashed lines and a little top hat symbol showing moderate turbulence. Here is 180. That's the top, because there's a line below 180. So the top of the turbulence is 180. There is no number below that line, so the bottom of moderate turbulence would be the surface. So it's answer number 1, moderate turbulence, surface to 18,000 feet.
873, the band of IFR weather associated with the cold front in the western states, as depicted in figure 55, is forecast to move.
Well, I'm trying to find this. It's on the lower left-hand panel here, the band of IFR weather having to do with the cold front. There's an arrow here with 30, so it's moving to the east at 30 knots. That's answer number 4, eastward at 30 knots with continuous snow, and the snow is just due to, or showing by these 2 asterisks on the panel.
Question 874, at what altitude is the freezing level found over southeastern Oklahoma on the 24-hour significant weather prog?
Well, we need to find the 24-hour side. Remember, those are the right 2 boxes on figure 55, and when we find the right box, we are looking for a dashed line which has to do with the freezing level. Southeastern Oklahoma would be the very tip, and that would be this dashed line. We just follow this up until we find a number on it, and it shows 120. So the freezing level is 12,000 feet. That's answer number 4, 12,000 feet.
Let's move on to question number 880 on page 72. The base and tops of the overcast layer reported by a pilot in figure 57 are?
Okay, we look at figure 57 here, and we can find the pilot weather report, which is what they're referring to. We need to find the base and tops, and we can see it says UA is pilot report over Oklahoma City to Tulsa, so he's on a route from Oklahoma City to Tulsa at time 1800 Zulu, flight level 12,000 feet, type beach 90, sky 12,000 or 1,200 I should say, broken to 5,500, and then it's overcast going off to the left, overcast from 7,200 feet to 8,900 feet, and that's what they're asking for. So it's answer 4, 7,200 feet MSL and 8,900 feet MSL.
Question 881. The winds and temperature at 12,000 feet MSL as reported by a pilot in figure 57 are?
Well, again, figure 57 is that pilot report, so we follow along after we just talked about. It says clear above, TA is temperature -9, wind velocity 090, true, 21 knots. So it's answer number 1, 090 at 21 knots and -9 degrees Celsius.
Question 882. If the field elevation is 614 feet MSL, or mean sea level, what is the height above the ground level of the base of the ceiling in figure 57?
Remember, a ceiling is defined as the lowest layer of clouds that's broken or overcast. So we need to find the lowest layer that is either broken or overcast, and on that pilot report it says the sky conditions are 1,200 feet broken. So the base of the first ceiling, or the base of the ceiling, is 1,200 feet ceiling. So they tell us that the field elevation is 614 feet. We would just subtract 614 feet from 1,200 feet because 1,200 is MSL, mean sea level, and that's 586 feet above ground level. Answer number 1.
883, the intensity of turbulence reported by the pilot in figure 57 is?
We need to find the turbulence section, starting with the letters TB for turbulence. Turbulence is moderate from 5,500 to 7,200 feet. So the answer is 2, moderate turbulence.
Question 884, the intensity and type of icing reported by the pilot in figure 57 is?
We find the section that starts with IC or ICG for icing, and we find that it's light to moderate, and then reading off to the left, it's clear ice. So that's answer number 2, light to moderate clear ice.
Question 885, what is the direction and speed of movement of the radar return at A in figure 58?
Figure 58 is an excerpt of the radar summary chart, and we need to find, they're rather difficult to find these letters, but letter A is off to the left here, and the movement is shown by the typical wind flag. So the movement is from the west to the east. Each line is 10 knots, each half line is 5 knots. So it's moving to the east at 15 knots. That's answer number 2.
886, what does the dashed line enclose at B in figure 58?
Well, we'll find letter B, and we find our dashed line. It's kind of a rectangular area, this dashed line, and that just says that it's a weather watch area. Answer number 2.
887, what type of weather is occurring in radar return C?
We find weather return C is down by the Florida Peninsula, and we see the letters RW plus. It's rain showers, heavy rain showers by that plus, so it's answer number 4 for heavy rain showers.
Question 888, what is the direction and speed of movement of the radar return at D?
D is found down by Louisiana, just off the coast of Louisiana, and we see an arrow pointing to the northeast and a 20 by it. That's moving to the northeast at 20 knots. So that's answer number 3.
Our last weather question is question 889. The maximum cloud top at D is?
Well, we've already found D down by Louisiana. We need to find a symbol showing us the tops, and that's this 300 with a line underneath it and then the dash or the line going down to where the top was. So the tops right here are at 30,000 feet because you add 2 zeros. So it's answer number 3 for 30,000 feet.
Thanks for your time and attention in this module. You'll notice we didn't answer every question. We've let some of them go. The ones we didn't answer deal with gliders, balloons, and helicopters, which Jeff and I are not qualified to teach because we don't fly them, and it isn't the goal of our course to teach anything but the airplanes. So good luck with weather. You might want to go back in your book and work all these questions on your own. Like I mentioned, we're going to pick all this up in the sample exams at the end of the course, so you might want to just move on to the next module.